pleasure to give a talk, and I will talk about the coherent sheaves, superconnection, and a formula of Riemann-Roch-Grothendieck. This is based on a joint work with Jean-Michel Bismut and Zhaoting Wei. First, let me state the main result of our paper. I will not go to the technical detail. So in my talk, X will always be a compact complex manifold, and I will consider Kx the Grothendieck group of coherent sheaves. Of course, here coherent means the analytic coherent sheaves. And I will consider the real Bott-Chern cohomology, of degree pp. And let's state the main result of our paper. In our paper, the first step, we said that there exists a Chen character map from the K group of X to the cohomology rings. Here, the K group, I said it's a group, but actually there is a ring structure such that the Chen character is a morphism of rings. This Chen character generalizes the classical Chen character in the following sense. If F is locally free, that means F is defined by local sections of holomorphic vector bundles. Then the Chen character is just the classical Chen character. In general, if F is a coherent sheaves, the 1-1 part, I recall that the Bott-Chern class has a degree pp. If I take the 1-1 part, then the Chen character is just the first Chen class of the determined line in the sense of Knudsen-Mumford. I recall you that the determined line of Knudsen-Mumford is defined for any coherent sheaves, and the determinant is a holomorphic lines on a manifold. So here the C1 is taken in the classical sense. So in this sense, our Chen character generalizes the classical Chen character. And the second part of our theorem is a formula of Liminal-Grothendieck. If we take a holomorphic map between two compact complex manifolds, so there is a direct image on the K group. There is also a direct image on the cohomological rings. Here, the vertical flash is defined by the Chen character twisted by the dot class. And our Riemann-Roch-Grothendieck formula just said that this diagram commutes. So this is a statement of our main result. Let me give you some historical remark. Of course, the first theorem is given by Grothendieck in the case of X, Y are projective. After Grothendieck, there are a lot of works, and I just cite the most important one given by Green, Delidon-Tong, and Levy in the 80s. And most important recent work are given by Julien Guivaud and Xiaojun Wu. In Guivaud's work, he assumed the cohomology ring is a rational delinear cohomology. And in Wu's work, he considers the rational Bott-Chern cohomology. But in both of these two works, I assume F is projective. That means that F has a factorization. F is a map from X to Y. There is a factorization from a very big projective space. And our work is going to remove this kind of assumption. And of course, the proof is, our proof is completely different with the one given by Guivaud and Wu. So let me first tell you the main step of our proof. So of course, the main step is indicated by Grothendieck. So we first consider we factorize the holomorphic map from X to Y. We write F as a composition of the map I and the map pi. Here I is defined by the graph and the pi is defined by the second projection. So Grothendieck suggests to consider the factorization on the K group and also the factorization on the Bott-Chern cohomology. And then the proof of the Grothendieck-Liminal theorem consists first to show, the first step is to show this part is commute. And the second step is to show this diagram commute. And of course, the third step is to construct the Chen character in the Bott-Chern cohomologies. And the first step is to show this part commute, and the fifth step is to show this part commutes. So, okay, so can you? I'm not sure it's probably I should attack this. Okay.
It's okay.
Yeah, it's okay. Okay. Yeah. Okay. So in the rest part of my talk, I will first sketch the first two parts. These two parts are very classical and known long before our paper. And then I will give you a very detailed the construction for the Bott-Chern cohomology. And I think I will have no time to explain the Riemann-Roch-Grothendieck's formula in the case of embedding. And this is based on an argument of deformation to normal cone. I think most of people here are expert on this. And then I will explain to you the Riemann-Roch-Grothendieck formula for the projection pi. This is obtained by the hypoelliptic deformation. Elliptic deformation. Elliptic deformation given firstly by Bismut in 1912. Okay. The construction of Bott-Chern cohomology is based on a recent work of Jonathan Bloch. So let me begin with tell you some notation. Here I will use the Tx and the Ts bar for the holomorphic and the anti-holomorphic tangent bundles. And I will consider the exterior algebra of type P and Q, which is defined by the exterior algebra of holomorphic and anti-holomorphic bundles. I will use the notation OX for the sheaf of holomorphic functions and the OX infinity for the sheaf of smooth functions. Then I will sketch very quickly the part on the Bott-Chern theory. Now I take a PQ degree P and Q, and the complex Bott-Chern cohomology of degree PQ is defined by the closed smooth PQ form quotient by the DD bar exact one. And there is a natural complex conjugation on the cohomology, Bott-Chern cohomology rings, just defined by the complex conjugation on the smooth forms. And it sends degree PQ to degree QP. In my talk, I will consider the real Bott-Chern cohomology in the sense that it's invariant by complex conjugation. And I will also just consider the degree with equal degree. That means the degree P equals to Q. And let me remark that in the definition of the Bott-Chern cohomology, we can replace the smooth section by distributions. By distributions, you will end up with the same cohomology rings. This can be proved using the elliptic operators. Okay, so this is a Bott-Chern cohomology, and let us look at the direct image and the pullback on the Bott-Chern cohomology. Now, I take a holomorphic map between two complex manifolds. There is a pullback at the level of smooth forms, and since the map is holomorphic, it is compatible with all the holomorphic constructions. In particular, it induces the pullback on the Bott-Chern cohomology. Now, if I take the dual of this map, it sends the dual form on X to the dual form on Y. And as we know that the dual form is just the current, in this way, we can define the direct image at the level of current, and it induces the direct image on the Bott-Chern cohomology. Now, there is some functoriality property on the Bott-Chern cohomology. Namely, if I take two holomorphic maps, there is a pullback at the level of smooth forms, and it induces the functoriality on the of pullback on Bott-Chern cohomology. And if we take the dual, we get the functoriality of the direct image on Bott-Chern cohomology. So in this way, we show the commutative part of the first part, okay? And let me sketch the proof of the second part. Okay, so this is based on the construction of the derived category. So let me take a coherent sheaf on X. So of course, coherent means that it's a coherent sheaf of OX modulo. That means that locally, our sheaf has a free resolution. That means for any X, there is an open neighborhood of X, such that when restricted to U, our sheaf has a free resolution of finite length. And the K group on X is the abelian group with the generator of the coherent sheaves, and the relation is generated by exact sequence. So this is a K group. And to define the morphism on K groups, I will need to introduce the derived category. The derived category, I will use the bounded derived category with coherent cohomology. That means the object in our category is the bounded OX complex. Here, bounded means that our complex is from some, begin with some finite degree R to some finite degree R prime. OX complex just means that for each degree is an OX modular. And our differential V commute with multiplication by holomorphic functions. Okay. And with coherent cohomology just means that for each cohomology group is coherent. I will not tell you the morphism in the derived category. You can understand the derived category is some category with universal properties such that the quasi-isomorphism are invertible.
Is this equivalent to the bounded derived category of coherent sheaves?
No, it's not. In the case of general complex manifold, no. But in the case of projective manifold,
okay.
Yes.
Okay, thank you.
Okay. So a most important construction on the derived category is the cone construction. That means that if we have, so it's a morphism of complex, morphism of OX complex. That means that phi preserves the degree EP to EP bar, and phi commute with differential. V is my notation for the differential. Okay. And so once we have a morphism of complex, so there is a associated cone. The cone is a complex. The cone is of degree P is defined by the P plus 1 direct sum with P, and the differential is defined by the V bar, and plus or minus depends on the degree of the phi. Okay, and thanks to this relation, we can show that the square of this is 0. So this defines a differential on the cones. And the cone is satisfy this kind of exact sequence. And now we can define the case theory of the derived category. The generator is just the object in the derived category, and the relation is generated by the cone construction. And it's very easy to see that the K group on X coincide with the K group on the derived category. Here, the flash is very easy to, I can tell you the isomorphism here. If E is some coherent sheaves, so it maps to the trivial complex. And if we have a complex here, it just maps to alternating summer on the cohomology, summer of P. Since the cohomology is coherent, so this alternating summer makes sense in the K group. And now we can talk about the derived functor. And if we have a holomorphic map between two compact complex manifolds, by Galois's theorem, the direct image of a coherent sheaf on X is still coherent on Y. and then use a universal property on the derived category. There is a derived functor defined on the derived category. I will not tell you the precise construction, but if each degree is soft, then the derived direct image coincides with the direct image itself. And for general element here, we need to take a soft resolution. So I will not go to the detail. And one important property of the derived functor is that it preserves the Gaunt construction, and then thanks to this identification, the derived direct image induce morphism on the K groups. And then there are some functoriality properties. Namely, if we have two holomorphic maps, then the derived product is canonically isomorphic to the product of the derived functors. And when we pass to the K group, we get the functoriality on the K group. And in this way, we get the proof of the second part. And as I mentioned before, these two are known long before our paper. Actually, I think this is go to 60s and this part is go to 70s. And now, let me give you detailed construction of the Bott-Chern characters. So let me go back and I will slow down. Okay, so the third part is construction of the CHBC on the K groups. So let me first recall you something of the superconnection. Superconnection, which first is developed by Quillen. Now let me take a vector bundle on X. I assume that E is a Z graded smooth vector bundle of free X. This is an anti-holomorphic exterior algebra modular. Okay, let me explain this. So Z graded means that E can be written as the sum of EI because it's a finite dimensional vector bundle. So it's from some degree R to some degree R prime. Lambda TX anti-holomorphic modular means that this is a graded modular. That means that if we have some map degree I, tensor with XEJ maps to EIJ. Okay, so this is there is some graded action and satisfies some usual multiplication compatibility. And now free means that there exists D. Actually, this some kind of exists some unique some graded vector bundle from some degree to some degree a smooth vector bundles, such that our E can be identified to the exterior algebra graded tensor product with D. This is identification of lambda modulo. Okay, so this is what I mean free. Free just means that just locally E is just some copy of the exterior anti-holomorphic exterior algebra. And I just remark that this identification is non-canonical. Just like the usual free modular. Okay, so this is our object, and then I can define the superconnection on E. Okay, this definition is first introduced by Quillen and then used in the paper of Jonathan Bloch. That A is a smooth section, sends the smooth section of E to smooth sections of E plus 1 is a anti-holomorphic, I will call it the flat. Probably I will take A prime prime to indicate its anti-holomorphic flat superconnection. If the first is it satisfies some Leibniz formula, so A prime prime alpha S equals to d bar alpha times S plus minus the degree of alpha alpha A prime prime S. Here alpha is some anti-holomorphic forms on X, and S is just the elements, smooth sections in E. And here, the multiplication comes from the modulo structure here. Okay, so the first condition said that A prime prime satisfies the Leibniz formula. And now the second part means the flat just means that the square equal to 0. Okay, so this is a superconnection in the sense of Quillen and Bloch. And now let me give you some example. The first example is that if D is a complex of holomorphic vector bundles, this is a complex of holomorphic vector bundles. Holomorphic means that each DI is holomorphic, so there is a degree preserving holomorphic structure such that D prime equals to 0. And complex means that V square equal to 0, and the complex of holomorphic vector bundle means V are holomorphic. That means D prime V equals to 0. And use these two objects, if we can take E is equals to the exterior algebra tensor with D, so graded, here is a graded tensor, okay? And the A prime prime is just V plus nabla prime. And you will see that this three condition implies the square of A prime prime equals to 0. So this is the first example. And the second example comes from deformation of complex structure. So let me take a deformation complex structure, or I will prefer call it it's a family of manifold, complex manifold X. So this is a submersion. And then I can consider the total space of the Dolbeau complex. This is the total space of anti-holomorphic forms. And I can consider the total Dolbeau operators. Okay, and if we choose a horizontal direction, for these fibrations, then we can identify this with smooth sections on D with the exterior algebra. Tensor with the fiberwise Dolbeau complex. And then you will see that this is just the E, and this is just the D. The only difference is that here the E and the D are infinite dimensional, but in our definition here, E is finite dimensional. So formally, this is just some infinite dimensional analog of our object. And this operator, if the Dolbeau operator, if we use this identification, you will write down explicitly this object as A prime prime here, and it becomes a superconnection on the infinite dimensional vector bundles. Okay, so these are two examples. And now we return to the general case, and let me recall you that there is a non-canonical identification, non-canonical identifications of the X tensor with D. But if we fix a non-canonical identifications, then we can write the A prime as a sum of V0 plus anti-holomorphic connections plus V2, V3, etc. Here, Vi is just sections of degree I of X with endomorphisms of D, but the degree is minus I plus 1 because the total degree is 1. And nabla prime prime is just a connection in the anti-holomorphic directions. And then A prime equals to square equal to 0 is equivalent to say that V0 equal to 0. And that prime prime V0 equal to 0. And the degree 2 part means that the square equal to plus V0, the anti-commutator of V2, 0, etc. Okay, so this is, I write explicitly the square equal to 0. And you will see that if this expansion end with just these two guys, we find that V0 equal to 0 and the commutator is 0 and this disappeared. So this equal to 0. This means that the D prime prime defines a holomorphic structure on the D part. Okay, so this is a superconnection. And now let me introduce two categories. Definition. These two categories introduced by Jonathan Bloch. So I will call
Sure. So I have just one question. So in your definition of A prime prime, so why there is no V1?
V1 is absorbed here.
V1 is
this is a connection, but if the connection shifted by V1 is still a connection. So I put this together.
Okay. Thank you.
Yeah, okay, so let me introduce two categories. The first category I will note the BX. The object is just the object, finite dimensional object, which I introduced before, the E equipped with anti-holomorphic superconnections. And the morphism in BX between E and A prime prime, and another object A prime bar is given by the global sections on X with endomorphisms of, it's homeomorphism. Homeomorphisms of E and E bar. Okay, and here E and E bar are free lambda modular, so I will take it to be degree 0 and commute with multiplication by exterior algebras. And I will also assume that F commute with differentials, with superconnections. Okay, so this is the first category. The second category is the homotopic category associate. The homotopic category of BX. And so it's with the same object as before, but the morphism on B bar is the quotient of the morphisms in B. Okay, and here I said F1 is equivalent to F2 if and only if F1 minus F2 is equals, as you can guess, is equals to the some homotopy relations. And H is some smooth sections of degree -1, okay? And it preserves the lambda modular. Okay, so this is the associated homotopic category. And let me state a proposition, which really this proposition related some algebraic construction and the analytic argument. So if F is in the homeomorphism of Bx from E A prime, E bar A prime prime, Then if we fix with this can be written as F1, F2, etc. Okay, and then I said that then F is isomorphism in the homotopy category if and only if here the F0, the zero part induce morphisms on the D0 part, on the D part, because it's degree 0 from D to D bar. But D equipped with V0 becomes a complex. So F is preserves the complex because F preserved with superconnections. And this theorem said that is equivalent to for any X in X, and pointwisely, this is a quasi-isomorphism. So it's really this kind of proposition related to the algebraic construction here and some analytic argument here, because we get some pointwise version. You will see this relation later. Okay, and now let me explain to you two fundamental theorems of block. The 3.2 theorem of block. The first theorem is a local result, which said that if prime is in Bx, then for any X in X, then there exists an open neighborhood X such that when restricted to U, this is isomorphic in the category of Bx to some holomorphic object tensor with some du, okay, and V0 plus D prime prime. So this stop at 2. So as we have seen that if the superconnection stop at degree 2, this is some holomorphic object. Morphic. Okay, and so this means that probably I should have said that this guy is holomorphic. So this theorem said that locally the block's object is holomorphic, and the proof is based on the fact that A squared equal to 0. I will not go to the detail. The proof is very similar to the proof of Newland-Deck theorem and this integrability theorem. Okay, and thanks to this theorem, we can construct a functor from Bx to the derived category with coherent sheaves. Here, you take an object E and A prime, then it sends to a sheaf, to a complex of sheaves. So over a small neighborhood U, so it's, the complex is just given by C infinity U point. And the superconnection here restrict to U and C infinity to U E dot plus 1. So this is the complex of sheaves. And as you can see that because A prime prime is flat, so this is defined a differential. And thanks to the Leibniz formula of the A prime prime, this defines a complex of OU complex. So this is some guy in the DBCOH. Okay. And now it's not difficult to see that this factor is to Bx bar to homotopy categories. And now I can state another theorem of block. It said that B bar X, this functor is an equivalence of categories. To be more precise, it's the equivalent of triangulated category. That means it sends the cone here to a cone here. So it preserves all the constructions. And thanks to this theorem, we have a differential geometric interpretation for the element of DBCOH, namely using the superconnections of Quillen. Okay. So Now I can talk about the Chen characters. Don't forget, so our aim is to construct the Chen characters on the K group. So we can, thanks to this theorem, we can completely forget about the DBCOH and work directly on the superconnections. So I said the DBCOH on BX. Now to construct the Chen character, let me recall you very quickly how to construct the Chen character on holomorphic vector bundles. So I will sketch these constructions. Okay. So if we have a holomorphic vector bundles, to construct the Chen character, we need first to construct the Chen connection. Now let H be a Hermitian matrix on D. Use this H, we can define the Chen connection. That means we can construct the holomorphic part nabla prime. Locally, if nabla prime prime is D bar, nabla prime is just the conjugation of the D operator with respect to H. And the square of nabla prime equal to 0, and the square of nabla prime prime equal to 0. And the curvature of the Chen connection is given by the anti-commutator of nabla prime and nabla prime prime. And I recall that this is some 1-1 form on the manifold with values in endomorphisms of D. Okay. And now the Chen character is defined by the exponential of the curvature with some kind of normalization. And the trace is taken in the endomorphism of this. And a priori, you will get smooth forms on X with complex coefficient. And the theorem of Bott-Chern said that the Chen character is indeed declosed and in its degree PP and its real PP form. And its class in the Bott-Chern cohomology is independent of the choice of the Hermitian matrix. So this is a classical definition of the Chen character. Now we need to look at how to define the Chen character for the elements of Bx. So probably so this consists of 2 steps. The first step is construct the so-called matrix on E, and then the second step, of course, is construct the holomorphic part of the A prime prime. So first this is the matrix on E. So first let's try to understand the matrix on the D dot. D dot is a complex. So definition is that maybe I just let H be a matrix, Hermitian matrix on the D dot. That means that H is in some smooth sections of X with values in D star tensor with D star due. Okay, and because H is some Z grid, I will assume to be some Z graded Hermitian matrix. That means that actually H preserves the degree. That means it's in Di star tensor with Di star bar. It's in the sections of these smooth vector bundles. And I will assume it's Hermitian, means that UV equals to HVU, take the complex conjugations. This is a matrix on D. Now I will try to generalize this matrix on E. So definition, H is a matrix, Hermitian matrix on E dot. I will fix some kind of non-canonical identifications. Okay. If the first H is in the E with complete exterior algebra, it contains the holomorphic part and the anti-holomorphic part. Then tensor with D star bar. And now I will have 2 conditions which generalize this kind of 2 conditions. The first is H is some degree 0. and the second is H is self-adjoint. I will not tell you the precise definition of these two, and you can understand these two as a generalization of these two kind of conditions. So this is our condition for the metric on the lambda modular, and I just remark is that a metric on D induce a metric on E. Okay, so I think this is clear, because if we have something here, it's you can consider this element as elements here just by taking taking to be 0 for the degree bigger than 1, and this kind of metric will be called the pure metric. Okay, now we have the metric, so we can define the A prime. To define the A prime, we need a pairing. So for alpha, beta, first I take the differential forms, and let me define the pairing between alpha and beta. This is defined by some normalization coefficient. So there no integration over x of alpha tilde wedge beta bar. Here, beta bar is just the complex conjugations, and the alpha tilde. So alpha tilde is defined by the anti-evolutions alpha p tilde is equal to minus alpha p minus alpha p minus 1, etc. just to where alpha is degree 1. Okay, so this is the definition of alpha tilde. A fundamental property on this bilinear form is that first it's Hermitian. The coefficient I here is just to make it Hermitian, and it's non-degenerated. And also the adjoint of D bar is D. Okay, I make this remark is just to remark the similarity between the D bar here and the D here. Okay, and now I can generalize this. If alpha beta are sections with values D, and H is a metric on E, then I can define a pairing between alpha beta as the same constant and the integration over x of alpha tilde wedge H beta bar. Let me explain what's this. So beta is as in values of the D, and H is take values of exterior algebra D star and D star bar. So if you H acts on beta, that means we kill the D part and the D star part, and then you will end up with some element of the forms, but take values of the D bar star. And if you then you take the bar here, finally you will find an object in exterior algebra of X with values D star. And alpha is in some things in D, so there is a natural pairing between D and D star. So this is a natural pairing. So the H, theta H is some form well-defined forms. And now I can define the A prime is the adjoint of A prime prime with respect to theta H. Okay, and this is well defined thanks to the fact that this is a Hermitian and non-degenerated. And of course, adjoint of D prime, adjoint of D prime prime is just D prime. This is thanks to the fact that the adjoint of D bar is D. Okay, so in this way, this kind of formalism generalizes the construction of the Chen connections. And now I can state this theorem. Probably I should first define the Chen forms. the CHE, which is defined on H, is defined by the some kind of the graded trace. It's called the super trace of the exponential minus the A prime, and then take some normalized constant I will not explain. Okay, so this is our Chen characters. And now I can state our theorem is just the first is a CHHC is declosed, and in the space of PP real forms. Okay, and the second is that its class in Bott-Chern cohomology. In Bott-Chern cohomology is independent of all the choice. That means independent of the choice of the metric on E. But I cheating some things that when I take a metric on E, I make this kind of non-canonical identifications. And I should insist here that independent of H and of the non-canonical identifications. Okay, so in this way, the Chen character is well defined on the elements of Bx, and then it's relatively easy to check that this descends to the DBCOH, to the K group, etc. And in this way, we define the Chen character on coherent sheaves. Okay, so in this way, so now we can go to the proof of the, how many times left? Okay, now we can talk about the proofs of the R.R.G for projection. I will restate our theorem. So I will take M to be the manifold X times S, and I will take the P, the projection to S, and I will restate the theorem of R.R.G for projection. Is if E is in some K group of M, and then the Chen character of the derived direct image is equals to the direct image of the twisted by dot class of Tx in the CH of E. Okay. So this is the R.R.G for the projections. And let me give a remark is that thanks to Bloch's theorem, we can assume directly E is defined by superconnections. Okay, and as we know that the sheaf defined by the superconnection is defined using the C infinity sections, so it's a soft sheaf. And for a soft sheaf, we know that the derived direct image coincide with the direct image itself, since E is soft. Okay, and now let us look at this sheaf on an open neighborhood. If U is some open neighborhood of S, is a small neighborhood on S, and then we look at the direct image evaluated on this set. This is equals to the E P minus U, and the inverse image of this is just E of X times U, and it's equal to smooth functions of X times U with values in E. Okay, so this is exactly the same situation as in the example which I mentioned before for the deformation of complex structure. So I can write this as, so I will fix a non-canonical identification here with exterior algebra of M tensor with diagonal part D. And then this becomes smooth sections of U, and the exterior algebra of U tensor with the drum cohomology with values in diagonal part. Okay, and as we have seen before, that this is just infinite dimensional object E, and this is my infinite dimensional object of D. And the A prime operator on here induce an infinite dimensional superconnection on the infinite dimensional vector bundles. So basically, we can use the same formalism to define the chunk character associated with this kind of infinite dimensional object. The only difference is that now we are in infinite dimensional space. So some matrix calculation should be replaced by some functional analysis argument. And let me do this. So take a matrix on GTX and a matrix on GD. So these two matrices induce an L2 matrix on the space of differential forms. Okay, and now we have a L2 matrix on the diagonal part, and as I mentioned before, this you can consider this as a generalized matrix on E, and thanks to this, we can define the A prime just as before. Then we can consider the chunk character. So we should consider the the connection associated to A prime and A prime and A prime prime, and this becomes a fiberwise elliptic operator. Fiberwise elliptic operator. That means that it's an elliptic operator on this part. So the fiber is X, so this is elliptic. So we can define the exponential of minus D prime prime prime. This is a fiberwise semigroup, fiberwise theta operator. And now I can define the chunk character in the infinite dimensional case, which is defined for infinite dimensional vector bundles and with help of a GTX and a GD, just defined by some normalization as before. Take the supertrace of exponential minus A prime prime prime, and the supertrace makes sense because this guy is trace class. Okay, and now I can state the theorem is that this guy, just as before, is declosed and is a real PP form. And the second is class in Bott-Chern cohomology is independent of everyone, and actually it's equal to CH of the direct image R pi star E. Okay, so probably I just mentioned one word for the proof. The proof of the second part is based on the fact that if we use the block theorem, there exists an object, finite dimensional object on the base manifold BS, which corresponds to the direct image, because this guy is in the derived category on S. Okay, and then so there exists a morphism F from E bar to from the finite dimensional object to our infinite dimensional object, such that when restricted to points for any S, the induced pointwise morphism from the diagonal part, pointwise version, the pointwise version, the D and the V0 pointwise version is a quasi-isomorphism. So it's really this fact related to the algebraic construction of the block with some analytic tools like the Hodge theorem, something like this. And use this kind of quasi-isomorphisms, we can show this kind of identity. This means that our infinite dimensional construction coincide with the finite dimensional construction which I mentioned before. Okay, now I can state the theorem of R.R.G. Our theorem for the, so unfortunately I need to make an assumption at the moment. If dd bar omega equal to 0, omega is the 1-1 form associated to the GTX. Okay, so this is a 1-1 form, the canonical 1-1 form. Then the superconnection of this guy, I deform by a matrix, a parameter T. This defines the same Bott-Chern class, but as a differential form, this T go to 0 converge to some well-defined limit, some limit. And this limit is cohomology in Bott-Chern class to the desired form P star of dot CH. Okay, and in this way we can show the Riemann-Roch-Grothendieck formula, but under this kind of assumption. The proof is using the local index theorems. I think I will have no time to explain this, but I try to explain to you that how to remove this kind of assumptions. This is the hypoelliptic deformation. So the hypoelliptic deformation. The hypoelliptic deformation consists to enlarge the space. So our fibration is X to S. We try to enlarge this space. That means I just in a more bigger space. Here, chi is the total space of the tangent bundle. Okay, so this is much bigger than X, and we have enough room to do the deformations. And now we have an object E here. This is our sheaf, and we want to work with this vibration. So we need to find some sheaf on this space and whose direct image coincide with this guy. And actually, there is a map I. This is embedded by 0 sections, and we can consider the R star E here. This is a sheaf here, and by the functionality of the direct image, you will see that the direct image of this guy on S coincide with the direct image of this guy on S. So thanks to this, we can completely forget about this vibration and work directly of this vibration. And now this guy has a canonical resolution using the Koszul resolution, the Dolbeault Koszul resolution. I will not tell you the detail, but just mention that the total space associated to the Dolbeault Koszul resolution is given by the complete drum complex, and with values in the exterior algebra. The holomorphic exterior algebra comes from, I will call this pi, comes from the Koszul resolution and the tensor with the diagonal part D, and equipped with the superconnection, the pullback of the superconnection of Quillen, and the parts comes from the Koszul, that is the I, the contraction with the direction I. I is the canonical section of in the total space. Okay, and thanks to this, if you write this, we can rewrite this as what we have done before. It's C infinity S is the exterior algebra in the anti-holomorphic directions, and 10 times with the total space, and the exterior algebra comes from the Koszul and the tensor with pi star D. Okay, and now this is my new infinite dimensional objects, and this is my new infinite dimensional diagonal part. And actually, we can do exactly the same thing as before. But if you equip with an L2 matrix on this guy, you will end up with the same difficulty here. But the idea of the hypoelliptic deformation developed by Bismut in his green book consists to consider non-L2 matrix, just consider non-degenerated Hermitian form. This form is some kind of mixing of the L2 form with some kind of the pairing, which Poincare duality pairing, which I mentioned here. And if you use this kind of non-degenerated Hermitian forms, you can overcome this kind of difficulties. And I think will have no time to explain this in detail. And I think I will stop here, and thank you for your attention.
Thank you. Thank you very much for the talk. And now it's time for questions or remarks. Any questions?
Yeah. So I have one question. So in the case one, it's a Kahler family. In the case one, it's a Kahler family. So for your proof, it will be.
It will be simple. It will be this one.
Yeah. So for the so you mean that so for the convergence of this one, we don't need to use the hypoelliptic.
Exactly. For the if you assume every manifold is Kahler, then you can directly use this kind of result. And this part is this part is the projection part is the same. I mean, in the proof of the Liminal-Roch-Grothendieck for Kahler manifold, you just you can just live in the elliptic world.
Okay.
For the hypoelliptic deformation is some tools for the non-Kahler manifold.
For the non-Kahler. Yeah. Okay. So so for example, okay. So in case one omega E is d closed. So in this case, we just use the heat kernel argument to prove.
Yeah, use a heat kernel argument. This is the standard way to show the ideal single index theorem. Use the heat kernel method of that.
Okay, I see. Yes. So I have another question. So you said so in the plane you have also an embedding of x to x times y.
For the embedding, yes. This uses the deformation to the normal cone. If you use the deformation to normal cone, essentially you can reduce to some projective embedding. That means that so we have the x embedding to y. And using the deformation to normal cone, you can reduce this kind of problem to some x to embed into some projective space as 0 sections. And then there is some explicit calculus on the projective space.
Okay.
So this is deformation to normal cone.
Oh, I see. So in this case. So essentially you work on the
projective essentially on the projective space PE. Yes, E is some holomorphic vector bundles on X.
Okay. Yeah. But in this case so for the parameterization of E over X, it's not a totally a product. It's
not a totally product, but
local product, but it's okay.
Locally, it's product. It's a holomorphic vector bundle. Local product is okay.
Local product, so it's sufficient. So for
exactly. Yes.
Okay, I see. Thank you.
So actually, you can once we have this embedding, this is usually use a normal bundle of X. We can essentially reduce to the normal bundle of X in Y. This is the holomorphic vector bundles. and essentially it's a projective space of this guy.
Okay. Thank you.
Some other questions?
So may I ask a question?
Yeah.
So how essential is this compactness condition? Like other than like it's used in Bloch's theorem, but like in your proof, like there's all this heat kernel kind of thing. Where do you need?
In the proof firstly for the first we can prove our theorem just assume that it has compact support. If you use the K group with compact support, so then the work then the other proof can go through. And for the non-compact manifold, there is a essential problem is here. Is this step for this kind of resolution by the Hilbert ZZG, this n is always finite and smaller than the dimension of x, but the dimension of this guy will become very big. And if the manifold has some covering, the dimension of this guy will become very big, and we will lose some control. So this is one difficulty in the non-compact case. And of course, the proof of this part, the proof of this part. So we have the pi star. This consists to the integration over the fiber. So to the integration of the fiber, you need the fiber to be compact to do the integration. So. And also we need the Gawat theorem is for the pop submersion. So so there's a lot of place to use capacity.
So it's not just like in the part of Bloch's theorem, like in the remaining part of your proof, also used compactness in an essential way.
So I can see that this part is okay. So if we x times y to x with fiber, so this is a fiber with x, right? And if we assume x is compact, then this part is this part can be this is okay. This part is okay. If we assume the Bloch theorem is correct, and then the Riemann-Roch-Grothendieck for projection is okay. It can go through. And if, for example, if we want to apply Gawat theorem, we just need the fiber to be compact. So the integration is still well defined because the fiber is compact, and this diagram is still always commute.
So basically, you are saying that even if the coherent sheaf, like it has a nice global resolution, even when the manifolds are not compact, but still you'll have some issue when you try to prove.
You need to assume the direct image has the same property.
I see.
You assume the coherent sheaf at the beginning has nice property of the and the direct image has nice property. Then we can show the Riemann-Roch-Grothendieck.
Yeah, let's say if the map F is proper.
It's not enough. It's not enough. You need to assume that the direct image at the beginning has a global resolution in the sense of Bloch, and the direct image has a global resolution in the sense of Bloch. Then you can say that the Riemann-Roch-Grothendieck holds true.
Oh, then the rest of the proof will go.
Because of the wait this sorry. Because in the sorry wait is I can't find it. Sorry where yes it's here, because in this part we should apply Bloch theory for the direct image. So you need so the direct image should satisfy Bloch's condition.
Okay, thank you.
Other questions?
Probably I have a small one. So can you explain, Shu, what is the philosophical reason why this is related to the end of your talk? So you said that by passing to the hyperelliptic Laplacian, you are able to
yes.
So this assumption that dd bar is equal to 0, if I understand correctly, in elliptic port, it appears essentially due to Liminal-Roch formula and the fact that
exactly, yes.
Why does what is philosophical reason why hyperelliptic?
So the philosophical reason is that you take, so you do not take the L2 matrix. If you take the L2 matrix, so at the end of the end, you will still get the Kahler form for this guy. If this is not Kahler, so this condition will not satisfy. So we cannot take the L2 matrix, and then you can take the Poincare pairing. Poincare duality, this which I mean the stupid pairing given here. And if you take here, you will get the D and the D bar operator, and you do the commutator, you will get 0. So this is not elliptic. So if you take this pairing, you will get something completely non-elliptic. And if you take the L2 matrix, you will get something elliptic. And the philosophy of the hyperelliptic is just modified the Poincare pairing. He use this is the Poincare pairing, and the hyperelliptic using the modified Poincare pairing by some Hermitian matrix here. Okay.
Yes.
When introduce of this omega x, so you will introduce extra derivation along the horizontal direction, and then the operator will become the hyperelliptic operator. And if you do this in the Liminal-Roch formula, you will still have some kind of difficulties. There is a dd bar omega x in the Liminal-Roch formula.
Yes.
So you will still have some problem. And the idea developed in this green book here is replace the omega x by the y square omega x. But you see that when this form restricted to x, this is 0. So finally, you will end up with y square times with this guy in the Liminal-Roch formula. And then if you use some scaling, some symbol calculator in the local index, this term will disappear.
I see. Okay, that's very clear. Thank you very much, Shu.
Some other questions? All right, there seems to be no more questions. So thanks again for the very nice talk.
Thank you.